Good. Our presentation this afternoon is disrupting technology with a 100-year building automation control network. And I don't know if you're like me, but I like to keep my customers. I work hard to get them, I work hard to maintain them, and I want to keep them there so I have repetitive business. But the way to do that is very simple. There's one little magic. All you have to do is build to last. When you put something together, a building automation system, you want to build it to last. A lot of people in today's market don't build it to last. They don't put in a system to make it last. They put in a system to meet the specified requirements. And they say, well, look, I got it in. It meets the specified requirements. And then they wait for 2 years for the warranties to wear out, and then they start making their money on the services. And that's okay, you can do that. But when you look at the requirements, you go, well, who put these requirements together? Well, there's some specifying engineer out there from a firm, and they're putting those requirements together. Now, where did they get those requirements? Who said their information is correct and that's the way to do it? Well, they in turn go to other standards and say, hey, look, this is what the standard said. Here's how I'm going to do it. And that's what they put in because it protects them. It protects them against liability because obviously if you're ever going to get sued on something and you say, well, I followed the standard, that takes liability way, way down because everyone's doing it. It's an accepted practice. So that's what you should do. But that does not necessarily mean you're building something to last. It just means you're building something. And the way to really build something to last is you have to make sure, get that GoToMeeting stuff here across the screen, is you have to look at the infrastructure, that building. And you have to say, how do I put the proper infrastructure in that building to satisfy the customer's requirements? What needs to be in that building to make that system operate? I've got an IoT, Internet of Things. There's lots of things out there, but how do I connect them up? And when I connect them up, how do I make sure that it's sustainable? So I need to use proven technology. I can't be using technology that's fly by night, just came about yesterday. I'm doing the building owner a big disservice. I need to put something in that I know will be there today, tomorrow, and the next day, and keep it going. And you have to be able to make sure that when you put those systems in, they're upgradable. Upgrading is different than being obsolete. We've seen that a lot of times now. You can see with computers a good example. Certain operating systems on your laptop, on your desktop, they're obsolete. You can't use them anymore. They tell you, we're not going to service them, we're not going to support them, don't use it. They're obsolete. You're not going to tell that to a building owner that you're going to obsolete everything in his building because you can't upgrade it. But what's interesting is when we look at the 100-year building, is we actually have 100 years behind us to see where we've come from. That's one thing fortunate we have right now is we can look back 100 years and see what's happened. And if you look at it and you go back 100 years, we're back in the roaring 20s. And by the way, welcome to the roaring 20s in 2000. Okay, but back then, the building automation systems, if they even had one, was probably a pneumatic system. It was air. In fact, air was the very first open protocol. No one controlled it. No one said how it worked. Everyone can use it. They knew how to use it. They knew what it was good for. It worked great. First open protocol. And of course, then there was electricity involved. So next thing that happened very soon after that is those pneumatic relays and switches were made electronic. They wrapped some wire around a coil, into a coil, put it on something, and now all of a sudden they made relays. So now they could take some of the actuation and then make it into a relay. So instead of pneumatics, they could use electronic relays. Of course, then they could put those relays together and start forming logic, AND gates, OR gates, and provide more functionality. Well, luckily, after the war in 1940, some guy came along and says, you know what? There's two things out there. One's called an insulator, one's called a conductor. I can make something right in the middle. It's called a semiconductor. It can conduct, it can be an insulator. Well, that was when we started what was a diode at first, turned into a transistor, the first electronic switch. Then someone had the great ideas like, let's put a lot of those electronic switches onto one little device. That was called an integrated circuit. It was actually all soldered together. In fact, you have to thank NASA for keeping the integrated circuit alive because they were the only ones that could afford it. An integrated circuit with minimal logic cost over $100 back in 1960. Can you imagine what's going on? Why did they want that? Why did NASA want it? Lightweight and small. Big deal when you're shooting rockets up into space. So they helped promote the integrated circuit. Well, once they started making the integrated circuit, some guys came along called Fairchild out there in Silicon Valley. And if you understand how Silicon Valley started, they put that together onto a substrate, and we had then the first integrated circuit, and then that integrated circuit turned into a microprocessor. Now we could put logic on a very small chip. The beauty behind that microprocessor was that all of a sudden we got into the 1980s, and guess what? Now we could start creating digital electronic controls, DDC systems. We could take that processor, have intelligence on it. We could now start doing control systems with DDC, direct digital control. That was working great. A lot of people embraced it. They started replacing all the pneumatics. In fact, you can see tremendous amounts of white papers out there that talk about, you know what, the benefits of converting pneumatic systems into a DDC system. They're still out there. They're still circulated, and people still have pneumatic systems out there, and you can buy controls. But that was the big thing that went on then, is that conversion over, that disruptive technology that converts us over now to a different way of doing things. But what happened then was all these OEMs, all these suppliers said, we've got our DDC system, but you know what? If you put our system in, you're locked into us. We kind of own that building because that's our equipment. Nothing else works with it. Nothing's interoperable with it. So a lot of times, those systems got installed at cost. Why? They made the money on the service contract. And if some of you are old enough, you probably remember some of this stuff. So the real money that was made was in the service contracts, not the installation of the system. Well, we come into the 1990s, and all of a sudden, we have distributed control systems. Someone said, you know what? Let's take those devices and let's make them talk to each other. This is the 1990s now. That was a big thing in the 90s. We can make things talk to each other. Today it's passé, but back in the 90s, that was the big thing. And to do that on an integrated circuit, to do that on a microprocessor, that was a huge ordeal. Another disruptive technology that came about, because all of a sudden now, what was architected in the 80s, the proprietary systems, closed systems, now became open. You could buy that processor, you could take the protocol, you could put it together, and you can make things interoperate. So interoperate. I can make my toaster talk to my thermostat. And by the way, it may not be my thermostat, I can get someone else's thermostat or someone else's thermostat. So that was the interoperability that went on. Huge explosion, the interoperability concept. And really what that bred then was peer-to-peer systems. Now, peer-to-peer systems is like me talking to you and you could talk to me. I don't have to go through an intermediary to get to you. I can talk to you directly and you can talk to me. And if I go on the PA system, I can do a broadcast. So it really opened up a lot of capabilities. We got into 2000, and all of a sudden someone says, well, you know, that's great, it's there, but let's open that up even further and make open protocols. Because in 1990, there was really there's some other protocols out there, but for distributed control, we're talking operating networks, control networks, not data networks. It was kind of like one protocol. So another protocol came out. First, it was LawnWorks, the protocol with Lawn Talk, and then BACnet came into being, and we had another protocol. So all of a sudden now, we can begin to speak multiple languages on that system. So it's not just one language, it's like what we have in the world today. You can speak German, you can speak French, you can speak Spanish, you can speak English. And believe it or not, who knows the number 3 spoken language in the world? I'll give you number 1 and number 2. Number 1 is English. Most of us are speaking English right now. Number 2 is an easy Spanish. What's the 3rd most spoken language in the world right now? Keep going, keep going. But you'll be surprised when I say it. Sign language. Fact check me on that. Sign language is the 3rd most spoken language in the world, more than Mandarin and some of the other ones. I was surprised because my guess was Mandarin. I thought it was Chinese. It's not. Sign language is the 3rd most spoken language. But see, now in control systems, we had the opportunity to speak more languages, do more things. So yes, Modbus is out there, Lawn Talk is out there, BACnet is out there. Now we can start talking multiple languages, and then we can open up those protocols so we can put those onto different platforms so we can speak multiple ways. It's not just one language. We can speak now multiple languages. So now my toaster can speak multiple languages to my thermostat if necessary, or to other devices if necessary. Really big for 2000. And of course, then we get past the 2010, and kaboom, Now we're taking all this data into the cloud. Holy smokes, now we're in the cloud now. And what's really neat, what did that is because thank you to the smartphone. If I can get in here with all the wires I got on. Thank you to this guy. I had a vice president of engineering one time slam his hand down on his desk saying, if you think I'm going to go to my thermostat and look at it and program it on a computer, you are nuts. Slams his fist down and boom, everyone jumps back. Well, he probably was right. I don't want to play with my thermostat with my laptop or my desktop. But by gosh, I love playing with it with this guy. I love opening my garage door. I love turning on my lights. Well, these are all things we could do in the 90s, but I really didn't want to do it with my desktop on my laptop. But this was a game changer, another technology that was introduced that just blew things up. So now all of a sudden we can access that data, we can do controls, and here is our user interface. Another disruptive technology change. So you can see here where we've come from with all of this. But in the last 100 years, what is the number one thing that happened here? What's the number one thing that happened over the last 100 years? Very simple. The number one constant is change. We went from having, pneumatic systems all the way up to, we're putting stuff in the cloud. Talk about technology change. Talk about changes all over the place. I mean, look at all the times you have to reinvent what's going on to be where we're at today. And there's no exception for today. But where does that take us for the next 100 years? You've walked around the show. You've seen what's going on out there. Tremendous amount of things are happening. There's still an explosion of all sorts of things being created, things being addressed, solutions being provided. It's not even ending. But what do? Well, we really need to look at the past to learn what to do for the future. Because the past, we can use how we've come from in the last 100 years to figure out our best strategy to get to the next 100 years. We've seen electronic revolution, okay? That's not going to stop. If you look at some of the technology that goes into some of the devices, it's pretty intense. I mean, circuits are getting smaller, processors are getting more powerful and smaller, which lends to a whole other set of problems when it comes to reliability and things like that. In fact, for some organizations that are OEMs, it's not the ability they can't design something. The real ability comes in, can you even manufacture it? Parts are so small, they're the size of grains of sand. Resistors, capacitors are the size of grains of sand. Integrated circuits got hundreds of pins that are underneath the part. Can't even see it. You really want to see it, you got to have an X-ray machine. So you got to know your manufacturing processes. Now, what does that mean? Well, it means reliability in the product. It's neat to put all that stuff in, but that product, the intensity that's out there in that controller, in those sensors, is phenomenal. That has implications. But the big thing you've seen here is that we've gone from air to the cloud. I mentioned that earlier. Tremendous difference in what we're doing and how we get there. But that's going to create a lot of confusion. So what do we learn from the past? Okay, I've kind of asked that question before, but what have we learned from the past that helps us understand where to go for the future? And it's really very simple, because you're out there installing systems, you're out there specifying systems, you're putting things into buildings. And what we've learned from the last 100 years, and the people that own those buildings, is that when they look at that building, they don't see that building as personal property, they see it as capital property. Talk to the accountants. What are they doing? They're capitalizing what's being put in that building. They're capitalizing that control system in there. That's not personal property, okay? That's real property that they can use. This is personal property. I probably will get rid of this in 2 to 3 years. In fact, Apple, that was part of their business plan, is that you're going to get a new iPhone, or if you're going to use something else, that's fine too. But every 2 to 3 years, you're going to replace this. Well, they realized that people were really liking what they had. The technology was so intense that really, I'm not getting rid of this in 2 to 3 years. I'm hanging on to maybe 3 or 4 years. For me, I'm cheap. I want to hang on for 5 years, get the money out of it, but I will get rid of it. Now, can you imagine going to the building owner and saying, you know what, I just installed this phenomenally great control network in your building, and in 5 years, I'm going to get rid of it? He's going to say, don't even quote it. Don't even quote the job, because you're not going to get it. So we have to look at things in terms of the control system has to last. And you guys know this. It has to go in with the intent that it's going to be there for 20 years because that building owner may not have the money, the capital, the expenses to replace it every so often. If you look at in your house, the furnace, a lot of times those furnaces, you look inside the design, they're only built to really be there for about 10 years. Oh, they'll give you some some warranties and all that, but the real materials that go into those parts aren't meant to be 20-year life cycles, a lot less. Now, if you get more out of it, good for you. And we can see some of those things because that 3 to 5 year life cycle is no longer acceptable. We have to be going for a 15 and 20 year life cycle. We have to build it to last. Otherwise, you're going to become enemies with your building owner, your customer, and your customer's not going to come back to you because he's going to be saying, you're pricing me out of the market with what I have to do. Now, in moving forward that, how do you put the infrastructure in that is sustainable? That's the big question here. We've got all this technology. It's blossoming, it's expanding, it's growing. We got another 100 years of what's going to happen next. So how do we begin now to say, well, how do we solve that problem? Well, it's pretty simple because we can break it down to some basic components. This whole picture of, oh my gosh, what's going on turns into, if we can just break it down to some fundamental components, we can get the answers. We can extract the answers out of those pieces. And those fundamental two pieces, when you get into a building, really fall under two areas. What's my physical media? How am I going to communicate all these devices? How am I going to communicate this? What is going to be in there to communicate on these devices with? We had a presentation this morning on smart cities, and we were talking about these exit signs becoming active displays for allowing you to know when to leave the building when there's a fire. Great, love the concept, it's great. My question was how to hook it up. What network are those signs on so if there's a fire, it's telling me, well, don't go out those doors, go out that door. That's all great, sounds good. But what's the control system? What is that media that's hooked up to those guys, and what am I using? So that's the first question you have to ask yourself when you make a building that's going to last for the next 100 years is, what is that media I'm going to use? We'll talk about that in a second. Of course, the second thing is, we talked about a little bit earlier, is, okay, I know the media now. I know that physical media I'm going to talk on. But what language is it going to speak? German, French, Chinese, sign language? What's it going to do? How's it going to communicate? And that's where you have to pick the right one so that it is also going to be, that language can be there for another 100 years. It can be upgraded, but it won't go obsolete. Now, we started out with the physical media. The physical media, we'll talk about that here, and really it's a little bit scientific up there, but it really falls into about 3 areas. When you talk about that physical media to make that stuff communicate, it falls into 3 areas. Very simple, just 3 areas. The first one is it's electrical. Let's get those electrons to wiggle on that wire, in this case a copper wire, and we're going to wiggle those to communicate. So that's copper wire, basically. So one of your best physical medias in the building to work off of is the copper wire. The next one is, the next media we could use would be some kind of electromagnetic spectrum. Well, that's a fancy way of saying, let's go RF. Let's apply RF technology to the solution here, okay? The next would be, you know what, those are nice, but you know what? Let's use something with light. That's fiber optic. So really, when you look at the physical media in your building, you can boil it down to saying, what do I want to put in for that customer? What does that customer need? Is copper wire the best thing? Is an RF solution the best thing? Or should we go light? Now, depending on how big that building is, the intensity of that building as far as what's in it, you may decide to use various flavors of any of these, okay? These are the options you will have. Now, some of these are better than others as far as what they can bring to the table. Now, of course, I mentioned the copper wire. When we look at copper wire, we're fundamentally looking at a twisted pair. And if you look at this copper wire, these are kind of the flavors you have to choose from in that copper wiring. The first area is really we have just 2 wires. It's a twisted pair. We've all seen twisted pairs, 2 wires. And there we've seen RS45, it's been around since 1980, that sort of thing. You can use it. But there's limitations on 45 because I don't know if you know RS45 much, you dive into electronics of it, but it's really a 3-wire system. It's not really 2 wires, it's 3. 2 is the data communication, but you're connecting electronic circuits together and you have to have a ground to make sure those circuits are at the same potential, the voltage potential. Otherwise, may not work, or may not work reliably. Okay, people don't realize that in an RS-45. Now, can I get two boxes to connect on 2 wires to RS-45? You bet I can. Luckily, if the voltages are right, I get that ground inherently in the system. But for a building, we're going to stretch across end to end. We got that phenomena of floating grounds. Okay, and it's a phenomenon. A lot of people look at floating grounds as a phenomena. It's not really a phenomena. It's really explainable because it's energy, and energy is pushing those electrons up and down. And voltage is really just a pressure. It's a pressure. It's a voltage pressure that's out there. And energy can cause that voltage, that pressure, to fluctuate and move around. Could be some energy from the sun. Could be the molten lava in the Earth's core. But these things can be fluctuating. Now, the best example is a lightning strike. Hit here, current runs through. It's basically there's a current flow, and you create potentials that way. But that's where the floating ground comes in, and all buildings have it. They call it a phenomena. It's really explainable, but you don't know when it's going to happen. It's hard to measure, it's hard to see, understand, but it is there. And that's where if you don't have that ground in RS-45, you could have problems. You will have problems. And by the nature of having that common ground between the two circuits, you will create a ground loop. I don't care what you do, how you isolate it, you're going to have a ground loop. All you're doing is minimizing it. And that's the big downfall of RS-45. It works great if you know how to control it and install it properly. If you don't install it and control it properly, no matter what you did, you created a ground loop in your system. And the question is, to what magnitude? And the best you can do is band-aid it with isolation and things like that. So we can get into what's called free topology. Free topology is a twisted pair. The nice thing is it overcomes that isolation issue. It allows us to have floating potentials and work. And it works very well. It's been proven for the last 30 years. People have been using free topology as a twisted pair mechanism to reliably transmit data. Of course, there's another twisted pair out there that some people don't realize, and that's your power line. Power line is 2 copper wires. We're going to cause electrons in those wires to sit on top of 60 or 50 hertz, and we're going to send communication down the line. And we have different modes of communicating with high definition power line, which we had a presentation on this morning. There's some other methods with home plug that do that same sort of thing, is to get communication to go on top of that 50 and 60 hertz component, and then we can communicate. So those are kind of, in a nutshell, our methods we can use for a twisted pair wire. And of course, now we can up the game. We can add a couple more pairs in there, and that's when we get into Ethernet. We can do 10 megabit, which is 10 base T. We can do 100 megabit, which is 100 base TX. And both of those have 2 twisted pairs. So you got 4 wires in there, okay? And that's how we can get the higher data rates. If you go up to gigabit Ethernet, you can go up even to all 8 conductors on a wire. So you have 4 pairs. But again, it's just we have 4 pairs of conductors with something like that. But you can see here, these are just ways to put it on copper. That's what's important. We're putting things on copper here. These are methods we can use to put things on copper because copper is very long lasting. Copper will last longer probably than an RF system. Now, when we get into that, that's what I mentioned the RF systems. We can put in that electromagnetic spectrum. We can put in things that we have today. Wi-Fi works great, love it, awesome. We can then do some more type of wireless personal networks, which is where we get into Bluetooth, Zigbee. And there's a technology called Thread that actually competes with Zigbee. It's the same thing. It's a mesh network, but it's called Thread. Thread was invented to compete with Zigbee. You don't see it so much here, but it's actually out there. But these are RF solutions for networks. Now, does RF represent the best solution for long-lasting applications? It's certainly easy to install, gets in quick, but will be there a long time. And is there any opportunities where the protocols used in RF will change, such that all of a sudden that protocol is no longer acceptable because it became obsolete? Have to be very careful on that RF side. Now we've seen the 2 methods. We can say, okay, what kind of physical media we want? And what we have to look at that physical media is then the installation costs for that media. Now, a lot of times when we bid a job, and for the building owner, the first thing we look at is installation cost. Okay, what's the cost to get it? I can afford it, I can't afford it. What sometimes those building owners don't see, and sometimes we try to hide a little bit from them, is the fact that, you know what, there's operating and maintenance costs. And in today's world, with the technologies that we have, Sometimes the operating cost isn't so much that, okay, well, I got a maintenance agreement, I've got upgrade agreements to keep the software current, but how do I run the system? I want to change a temperature somewhere. How can I get my librarian to change the temperature? Or when you talk about grade schools, K through 12, who's the person, K through 8, who's the person in that school that can say, I can get in there and manage that control network, or I can open up a port on the Ethernet so you can come in there and look it through a VPN. Who are those people that are doing that? If you've got a nice big building and they've got a facilities manager that's on budget, and hopefully he's trained in IT, maybe he can do it. Or maybe you have an IT department, and of course, then there's your biggest nemesis there, because those IT people don't want to play around with control networks or OTs. They want ITs, not OTs. So you got all those things to worry about. But that's the part that who's going to be able to work it, and especially when you get into smaller buildings, small boxes, small box stores, buildings that are maybe 5 to 20,000 square feet. Who's really going to run it? Do they have the expertise to run it? Because when you start going to them and saying, well, you know what, you've got to do a service agreement. Now, service agreements are good. Repair, maintenance, those are things are good to get set up. Responsiveness, you know, as a building owner, I would want that. So that if something happened on Saturday at 2 o'clock in the morning, I got someone to call. They'll be there Sunday morning, hopefully with the right parts. But for the majority of the time, I want to be able to control that system. I want to be able to change those set points. I want to be able to manipulate a few things. I just don't want every time I have to do something, it's a $200 bill or it's a $500 bill to bring someone in, sit there for an hour, tweak a few things and leave, and then I got a big bill sitting there. Can I afford it? That's the big thing. So the operating and the maintenance costs are very vital here, and they just keep going around and around and around. And this is where in the 80s, they capitalized on that aspect. Give away the installation, get you on the operating and maintenance. And that's how they made a lot of money in the 80s on. Of course, then, with technology now, we're involved in another aspect. What happens if it goes obsolete? What's the cost to rip it out and put something brand new back in? That's a big challenge there. Talk to the customer that, oh, you know, 15 or 20 years, guess what? You're going to rebuy that system again. You buy the whole thing all over again. It's not going to sell very well, so don't say that. But that's the reality. That's the reality, is that that's probably could happen if you don't select the right infrastructure and the right protocols to put into that system. And that's what we're here talking about today. It's exactly that. Now, when we look at those things, there's proactive ways to look at that. And you guys have seen some of this stuff here before. But when we talk about these systems and reliability, which they're not talking about that anymore. We forgot about these things. These things we learned for the last 30 years, we're forgetting about. And we have the, you know, mean time to repair. You know, how often do I have to repair that system? Okay, something's going to break. How often do I do it? Now, I told you earlier that technology is going boom. The complexity of these circuits is going boom. There's explosions everywhere you go. Who's talking about the mean time to repair? Because if this is a very intense controller or a very intense thermostat, first of all, I got to be able to figure out what is broke. Then I got to figure out what does that thing do, and then I got to be able to reinstall it in my system, and I got to be able to do all these things. Who's doing all that? Well, part of that falls into the next part, which is mean time to recovery, because it might be broke, and I know that once I get the guy on site, he can redo the wires, he can reinstall the box, he can get set it back up in the system, few hours. Okay, but when did I first discover something went wrong? And then how long it took me to figure out, okay, something's not right. This room's getting hot. What's going on? Oh, better make a phone call. Oh, guy can't come today. He's going to come tomorrow. That's all part of the mean time to recovery. This room's going to sit hot for a while until that person comes in and figures out what's causing this not to be maintain the proper temperature, whatever's going on. Of course, that's more the end of the person that's in the building. But then we look at mean time between failures, MTBF. That's actually looking at the product, saying, what's the reliability of that product? No one's talking like that anymore. That really came out of the aerospace industry because they were concerned about planes crashing. And they wanted to make sure they could get a repair schedule so they could beat when the potential failure of that part, that component would happen, and they wanted to replace it before that would happen. Now, when we get into buildings, no one's talking about that intense edge device and when it's going to fail. No, you need to get that intense edge device, put it in your system, look at all the cool things it can do as far as data transfer. Oh, when's it going to fail? I don't know. But boy, I got a PC sitting there. I got an embedded PC sitting there. Very intense piece of electronics. No one's telling me when's it going to fail and who's going to repair it and who's got the expertise to repair it. These are complications that we have in these systems. And of course, then there's mean time to failure, which is just like MTBF, but it's for parts you cannot fix. You got to replace it. Just pull it out, replace it. Okay, and there's devices out there that fit that more appropriately, maybe a thermostat or something. You can't repair the thermostat. If it's broke, it's broke. Rip it off the wall, put another one on, keep on going. But how often do you replace those thermostats, those sensors, those actuators, all that kind of stuff goes into that. And I already kind of broke some of this, what goes on here. This is the kind of a timeline of exactly what I talked about on that time to repair. As you can see, I got the mean time to repair, and then the top has the time to recovery. And as we go to our section, you have the part where you're actually, you have a failure notification time. And this is another piece that we talk about now when we do with IoT. This is some of the beauties of the IoT, in that now we can get these controllers to tell us things like, hey, something's not right. We're getting text messages, we're getting tweets, we're getting things that can be sent to us to say, something's not right, get in there and look at it. So now we're reducing, those controllers and those systems can reduce that time to recovery. And then because the person, it's the integrator, the person that's monitoring that system goes, you know what, that's all coming from that controller, something's wrong at there, or it's coming from that thermostat, that's where the problem is there. Now they can get to it quicker. They can get to the job site, they can do the repair, and all of a sudden the repair time goes down too. So these are things you've probably heard about the last 5 and 10 years about how we can reduce that time, so that by monitoring those systems, putting that data in the cloud, analyzing that data, when the person shows up, they get there quicker, they solve the problem faster, life moves on very nicely then. So it's very important to see this. So when we're out there talking, when you guys are out there talking to that building owner, you need to be looking at that picture and saying, how's that going to happen? When I go to that OEM, that controls house, or whoever's providing that product, you got to be looking at it and saying, how are you guys doing this? What are you doing to address those issues? How are you making that happen? That's very important, because if we forget about it, we're taking that last 100 years and going, gone, don't care, forget about it. Let's relive the history all over again. Let's do those mistakes all over again. That's where we talked about the MTBF with the products. Now you've seen that old famous, the bowl-shaped curve. These are products now. This is not that system. This is the product. And the bowl-shaped curve says in the very beginning when you build something, that's your early life. That's when you're probably most prone to having most failures. And that's true. As soon as it comes off that production line, it hasn't been tested. So you want that manufacturer to make sure they're testing, 100% testing, okay? So the guy says, no problem. I'm 100% testing. Don't worry. I've checked it. It works great. Put it in the box. Boop. Comes over from China. Well, one of the things they do for accelerated life testing, there's 2 things they do for accelerated life testing. One is you thermal cycle. You can thermal cycle to get out of that first part of the bowl there, get that early life out of there, say, you know what, I found any failures. So you can thermal cycle it. They do that. They can do that for 24, 40 hours, up and down in temperature. And I'm talking 50 degrees C swings, and they'll do that. This is how they make military hardened devices. Military is big on this. Aerospace is really big on this. That they don't even want that. You can't shoot a missile up and expect to say, well, I got early life failure. Oh, that's acceptable. It is not acceptable. People die, things get destroyed. Got to be gone. We got to be operating in the useful life of that curve. So they'll do that kind of testing. They'll thermal cycle. Another way you can also accelerate life is you can vibrate it. You can put it through some shock. Shock is boop, drop it on the floor. Vibrations, let's just shake it a lot. Okay. Well, 9 times out of 10, we're in building automation. We're not in the military. We're not in aerospace. We're not going to do that. So the manufacturer's going to say, well, I tested it. Yeah, it meets that requirement. It meets these parameters. Everything's working great. But I'm not going to thermal cycle it, and I'm not going to shake and bake it. So he doesn't. So guess what? They build the product. Product's built over in China. Guess what happens when it comes over from China? Shock and vibration, air travel, ground transportation, up to your doorstep with UPS. And I hate when the UPS pulls up by our facility. I hear the guy banging stuff in the truck. And we're like, I hope that's not my box. I hear him bam, bam, all over the place. But how many have been on the job site? I don't know, pick your favorite number, 10, 100, 20, 30%, or some number. Controllers or things just don't work. Right out of the box, it's not working. They're broke. Don't know why. We can theorize the cows come home, but actually one of the things they did from China over here is they just went through basically a life cycle test, an accelerated life cycle test. They were shaken. They were dropped. Shock. So is that the problem? Don't know. But that's part of the reason why sometimes when you get it, it's wrong. Not to mention it could be a quality issue where they just put the wrong stuff in there or something like that. But that's why sometimes when you're on the job site, it's straight out of the box from China and you go through that early life failure mode. So you get to play in that first part of the curve. How do you get out of it? Not much you can say. You got to work with your vendor on that. Who's giving you that product? What are they doing to make sure when you get that product, you're in the useful life zone? Now you don't want to beat the heck out of it, but you want to make sure you're in the useful life zone. What they do to make sure that I get it. Now, there's only so much we can do because UPS is going to still throw that box in the truck, but we can look at that. And of course, then we got the useful life. Now we're in that operating zone. And of course, after a certain period of time, then we get into the wear out section. And this is when you look at the electronics, because today that electronics is getting so much more intense. It's not basic stuff. It's very small micro electronics with very small solder joints, and it's very sensitive ESD, all these things. And yet they're coming out there saying, hey, no problem. This stuff's more reliable than the last stuff. This is great stuff. Oh, look at all the things we can do. What they're not telling you is what's really going inside, the intensity of the electronics, and what's the reliability of that kind of stuff. It changes the game. Just a case in point is the electronics is shrunken down. Things get miniaturized. They become more susceptible to noise. Okay? Because when you have something really big, try to put energy on it. It's very hard to do that. Make it smaller and smaller. You're creating antennas, and all of a sudden now, these small microelectronics become more susceptible to noise. Okay? So now we talk about having a VFD sitting next to you. Could that box, unless it has appropriate measures done to it, to be more susceptible? Yeah, it probably is. In fact, when the people that lay out the circuit boards for those devices, they have to be very knowledgeable of impedance matching, trace layout, all these things, because they're making multitudes of mini antennas inside there, and those things will pick up noise from anywhere and anything. So they have to become even more sophisticated to make sure these things processors operating at 100 megahertz, woo, fast, 500 megahertz, ooh, we got to switch. That these devices, if they can operate at those clock speeds, who's to say some RF energy operating at that same frequencies can't couple onto that circuit? The answer is yes, it can. It's more susceptible to what's going on. What's interesting as we move on is we get into the reliability of this physical media is the connectors. Everywhere we go out there, and it's good, I got them in our building, we're using RJ45 connectors. It's a great connector. That's where you can put our Ethernet on. But if you understand what goes into that connection as far as reliability, you kind of go, oh boy, watch out. Because who hasn't had an RJ45 where it broke? Okay? Now, when we look at that RJ45, really what we're looking at is the fact that you got a very nice pristine connection sitting there. It looks like it can plug in really easy, but really what goes into that is that you actually have a crimp connection. There's 8 wires in there, and I said we're only using really 2 pairs, unless we're doing gigabit stuff typically, but 2 pairs in there. It's got 4 wires that I have to be able to crimp. And when we crimp that, we're using insulation displacement. We're taking a copper V, sliding a wire in there and hoping then that V, as we press it in, just places that insulation, and that V makes contact with that wire. So we got a crimp connection. That's my first mode there. I got a crimp connection, okay? Well, now that I got that crimp connection, you'll see then that we come out to some tabs. These typically are some gold contacts, but there's some contacts. Really, there's not much spring force behind them. That's the connection we're going to make. Now, what's interesting then is with that, we have to slide that. And unfortunately, you can't see it. It's actually kind of dark in there. But if you look inside an RJ45, there's some other spring wires coming up. Basically, it's mechanical. It's a mechanical spring sitting there. So you're going to rub those wires up against that spring connection right there. So it's all mechanical force. So you're going to take 4 to 8 wires, and you're going to mechanically connect them after you've crimped them to a spring force. Okay? How long is that going to last? Now, typically, they will make connection. Okay, I'm really not seeing them not make connection, and they're typically gold-plated. You want them gold-plated. Why? Because what's going to happen with those connections is it's not so much that I'm going to lose the connection as I am worried about the dry circuit phenomena. Dry circuit phenomenon is very simple. It just means that that connection is touching, but because we get oxidation, corrosion, and dirt inside there, that develops a higher resistance connection. So I'm putting a 1 ohm resistor, a 2 ohm resistor, a 100 ohm resistor, all of a sudden a point where there's enough resistance in there where it's touching, but I can't get the electric continuity that I wanted. I have a dry circuit phenomena. Circuit doesn't work. That's what you're worried about with this mechanical spring force on these wires, exactly that. But that's not all. Because on the edge of that connector, that is a molded connector that actually came from the telecom industry. We're just adapting into our industry. But the biggest thing on there is that little piece of plastic knob that's sitting on there that holds it into the device. It locks it in. The manufacturer of that plastic, what they did is when that little tab went in, they necked it down at the very bottom there so that they could make that tab flexible. But they had to neck down that plastic so it could become flexible so it could snap in. But if they didn't and made it solid, you'd never be able to bend it. It wouldn't bend. Okay, what's the number one thing that's going to happen with plastic? It's going to dry rot. It's going to become brittle. Now we've got a neck down connection that if I start bending it too many times, it's going to break. If it becomes more brittle plastic and dry rot, it's really going to break and snap. And I guarantee you, once that little piece comes off, it's over. The connection's gone. Even the force of the wire that pushes it in can pull it right back out. And if anyone's tried to play with RJ45s with a broken tab on there, it's a pain in the butt. You don't want to work with it. Now, can you imagine that is up in the ceiling here? Go get it. Okay? Can you imagine if that's up in your rooftop unit, up in the outside, in the sun, the heat, the elements? Watch it break. Watch it fail. Okay? Those devices were meant to be in a server room where I have a controlled temperature, where I have a controlled atmosphere, humidity, things like that. They weren't meant necessarily to go up in a ceiling. They were not meant to go up into a rooftop unit outside in 130-degree temperature with humidity, heat, and cold and all that kind of stuff. They're meant to go in controlled atmospheres. Yet, don't put them out there. That's the big thing. Don't put them out there. How do you solve that problem? Well, we've got them out there. Just go to a regular connector, screw down terminal. That's the best thing you can use. A screw down terminal is the best thing you can use. And the terminal there on the left side there is a good one because all you have to do is take your twisted pair, bring it in there, screw it down, and that's probably your best reliable connection. The trade-off is on that is that sometimes people say, well, I got 20 wires and to pull those out, put them back in, that takes a lot of labor and time. So the trade-off is to go to more of a push connection or a plug. So I'll put those wires in, and if I have to disconnect it, I can pull the whole thing out, push it back in. Granted, I made another connection there, but it's still a very robust connection. You're dragging the metals inside there, and if you get the right connectors, it's still a very reliable connection as opposed to wire displacement crimping and the mechanical connection, and of course, broken tabs. So again, this is some of your next area. You got a quick question. I can see something's eating at you. You're exactly right, because even inside on this one here, inside here, there's a connection that has to be made with that pin. That can also corrode. Again, typically those are not gold. I guarantee you they're probably not gold. So again, you worry about oxidation, corrosion, things like that over the length of it. And yes, now that's when you have to really watch your manufacturer and what connectors are they using, because there's a lot of stuff that comes off from China that is different than other brands. Okay, that's one thing we watch very closely. Is we've had manufacturers come in our facility, and no, we're not interested. You know, we look at the reliability of that connector, and we go, we're not even going to play with it. We're not even going to play with it because that has to work. It has to work for 20 years, in that reliable sense. And that's where we're very persnickety on who we choose for connectors, because if you don't believe me, let's go to the industrial sector. Let's talk industrial Ethernet. Look what they use for connectors. It's nothing like this. It's much more intense, but it pulls us into a price category that we can't afford anymore. So all of a sudden now we've got a whole other set of issues we got to deal with. So if you want to learn about Ethernet, go to the industrial side for a while and see what they're using for connectors. Because I'm not saying anything wrong with Ethernet. I'm just saying, look at the connectors they're using for reliability. Gain that reliability and that robustness. It's not the same ones we're using here. That old patch cord you can run out to and just crimp together. They're not doing that. They are not doing that. So I would advise, and we've seen it already, I would advise you, don't just run out there and quickly crimp some wires together on your RJ45s, and you'll probably be back there in a month replacing stuff. You need to get some really good cables. If you're going to do an RJ connection, really good cables, be aware of these other things because they will be there. I don't know of any computer that I haven't plugged my Ethernet connection to that I haven't, at some time or another, at least somewhere, gone in and plugged in, plug it in and unplug it. We got a technician sometimes, but all of a sudden someone will have a connection problem, and what does he do? He runs around where all the routers are, all the gateways, and he just starts unplugging and replugging in, hopefully to find the magic connection that solved the problem. So that's where you're, The next thing is, we talked about the hardware. Remember I said the protocol. Now I want to try to keep this very simple because protocol can get really complex and over our heads it goes. Obviously, we've all seen the OSI model and the 7 layers. But really, there's 3 things we want to look at here. We want to make it very simple. There's an application that's running. We have some kind of protocol stack that's running the information down. And really what it's doing is taking out that physical media. So really just 3 areas we want to focus in on, because all the rest is detailed, and let's not worry about that for today. It's just not too much. So really it's just application, there's a stack, and the physical layer. What's most important about that is when we look at that application, again, we can derive some commonality out of these different protocols, out of these different languages that we can speak, because really what's happening with each one of those, if we look at BACnet, we're setting out an object. The object is all the parameters and the contents of that variable. The bottom line is it's the variable with information around it, okay? Then with that, we can also run services. So really, BACnet at the application level is objects and services. Pretty simple from an application standpoint. Now, don't get me wrong. We have an application running behind those objects and those services. So we have a fan coil, heat pump, thermostat, central plant, on and on and on. But the bottom line is the variables are objects. And with those objects, we can run services on BACnet. Pretty easy, okay? Same thing with Modbus. A little more different scenario, but again, we have addresses that has the data. We got to know something about what's in that address, scaling, and all these kind of things. And with that, we have some services, which are called function codes. Pros and cons to both, but the bottom line is we have some variables with the addresses, and we have some kind of services to run some kind of other features. And Lawn Talk is no different. Been around for quite a long time. And there again, same thing. We have network variables. If I can say a snippet 10p, and I know exactly what it is, the magnitude, how it's scaled, everything about it, because LawnMark has gone in and says, we're going to define what that is. There's no reason for each one of you to decide what it is, how it's going to be, and what's going to look like. We're going to take care of that for you. And that's a network variable. And of course, with that, then we have network management commands. We can add other features to what's going on here to make things operate better, see more information, do things. So really, there you go. They both have the same thing. We have the actual program, we have variables, and we have services at the application level. So that very top level, that's really what we're dealing with. Then we can jump into that stack that does its magic and sends it out the physical media. And that's kind of what I said here. So when you see this in perspective, this kind of makes it look fairly simple. So when we start talking multiple protocols, which is very important because that's where we're kind of going, is there's so many systems out there. We've had the last 20, 30 years of stuff being installed, and we start talking about devices that can speak multiple protocols. Well, that's what we want to look at as we see these things. You know, we want to look at, okay, there's our application, but how am I sending out those variables? Is that variable an object? Is it a network variable? Or am I sending something to an address that someone wrote on a piece of paper what that address is and what it should look like? Okay. Then we run it down the stack with all the neat things that stack can do. Where it's a BACnet stack, Lawn Talk stack, TCP/IP. Will that take care of all that other intricate stuff? And of course, just like we talked about, you have that physical layer. Now, one thing with control networks that we seem to have forgotten is that we got all these IT people talking to us, and we're talking a control network, an operating network. And the whole purpose behind those is small packets, but lots of packets, okay? It's not that I'm communicating at gigabit speed. That's not the issue. I don't need to communicate at gigabit speed. Tremendous overkill. What I got to be able to do is send lots of information. What's the temperature? What's the humidity? Is that switch on? Is that light off? What's going on over here? What's the status there? That's really what I want to communicate. So I want to send lots of packets and make them small as I can. That's what you're looking at. These are the fundamentals that are going on. The other thing we've kind of lost a little bit is single point of failure. I was at a little seminar this morning. They were talking about connecting buildings and people to IP. Holy smokes, we forgot about everything that's in this thing. Forgot about everything. Why? Switches and hubs and controllers that have switches in them. And all of a sudden, we lost this concept of a single point of failure. I mean, all it takes is one switch to go out or something go, and the whole thing's down. Or we start talking internet security, and we're running everything to some kind of server or something in the middle, a hub, that all the data is going through to make sure it's secure, that I'm not connected to my IoT or my IT system. And I'm going, if that guy goes out, what happens? Well, okay, we'll solve that. Let's make something redundant. Let's put something else in the system to make it happen. And all of a sudden you're going, where am I going with this? Can I maintain? In fact, that was one of the questions the guy asked us, how do I maintain this? You know what the guy said? Go hire an IT guy. I'm going like, that's what I need on my payroll, another IT guy. I'm trying to get HVAC specialists. I'm trying to get people that understand and know HVAC control and building automation. That IT guy doesn't know anything about building automation. I could teach him, but oh my gosh, another guy on the payroll just to do IT and set that stuff up? No. And he's the central hub of, does that job go in or not? Sorry, Sammy. I know Sammy over there's an IT guy. He's one of the few that's the cream of the crop. But that's what being a small company and putting in smaller operations, that becomes a hard sell to do some of that stuff. That system has to be able to install itself. It has to be able to be simple to install, simple to maintain, and you've got to have these attributes here. The other thing in these systems too is that the noise immunity. Again, when you look at industrial Ethernet, what they do for noise immunity, cabling, we're not even thinking about in building automation. You notice I didn't talk too much about secure. He goes, whoa, you missed that whole security aspect. You missed it. No, I didn't. It's not a problem if we do twisted pair. When you go Ethernet and Wi-Fi, kaboom, it's another problem. Everyone's going security, 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 hackers coming in, sending in malware. If I run a twisted pair, running free topology, high definition power line, who's going to hack into it? Who's even going to touch it? You can't see it. If I put a web server out there that makes everything connected to Ethernet, and all of a sudden the hacker goes, oh, I see a port over here. You know what? It's open. It's unsecure. He's going to get in there. He's going to come in and go, okay, I'm going to look for the accounting area. Oh, there it is. There it is. I'm going to drop my malware in there, and boop, I'm gone. Next thing you know, the person goes in there going, my server got corrupted. How'd that happen? Well, someone opened up a port so the person can come in and look at it from remotely, and they forgot to close it. The hacker saw it because he's just out there surfing like crazy, and he planted his malware. But when you're in a twisted pair network, it's like Windows and Linux. How many people are buying, spam and all the malware and security stuff for Linux? It's just like non-existent. Well, it's the same way when you get a twisted pair. No one's hacking it. And to get into it, you can't get into it. If I have Wi-Fi, I can see all your Wi-Fi. I can see all the Wi-Fi connections right here. This guy right here allows me to see everything. If I have Ethernet, I just need one of these guys, and I can see everything. So a student, anyone can get in there and start saying, I can see your system. I can see you. I can see if I can get into it. But when you got a twisted pair network or high definition power line, doesn't mean anything. Wi-Fi means nothing. Doesn't mean you can't have that for your edge device and to connect into it, but those problems just like disappear. They're off the radar screen. That's why I didn't talk about it, because I don't have those problems in those kind of situations. Now, yes, I'm going to want to put a web server in there, and I'm going to want to have a web page set out of my building. I'm going to be able to monitor stuff, but let's isolate that. If you make it your whole control system, good luck. Of course, the other area we start missing is peer-to-peer. I want, just like I said very early on, I want to be able to talk to you, and I'll be able to talk to you, and I want you to have the opportunity. If you want to talk to me, you can talk to me directly. I don't want to have to go through an intermediary to say everything I want to do to you, so I can tell you. That seems like what's happening here. We're always having to now go through an intermediary, go to some router, some hub, some security device, some master unit that allows me to make sure that I don't have any kind of corruption in my system. Where are we going here? We're going backwards. In fact, when you looked at some of these systems that are out there, beautiful systems, intense architecture, I just sit back and go, gosh, that's going to be a lot of learning on my behalf. Okay, I might be able to go over the learning curve. How am I going to tell a customer what to do? He's going to be totally lost, which, okay, that's good. I can get a service contract and I can maintain it. But then when it starts breaking down, or maybe I'm not there and the next guy comes in, he's not going to know the first thing about it because he doesn't know anything about that architecture. He doesn't know anything about that system. He doesn't know anything about that product line. He's going to have a problem. He's going to have a big problem. So that's where you have to look at the complexity of these things. And we've solved these things in the last 30 years. Some of the things that are offered by Lawnmark, the channels, the communication protocols, these things have been addressed and resolved. In fact, in our next presentation, Sammy over here is going to be showing you an example, a real world example of what goes on right here. So again, what we're looking at here, look at your infrastructure. Probably copper wire is a very good solution for a long-term building. Look at those connections to make sure they don't fail. It's a very important point. We forget about that real fast. Of course, field-proven solutions that are cost-effective and sustainable. We don't want them to be going obsolete. So we want to be able to upgrade, not obsolete our protocols. So I really haven't given you any answers here, okay? That was my purpose here. It was not to give you answers. It's to make sure you understand the last 100 years. So as you're putting in buildings for the next 100 years, you understand these things so you don't repeat the mistakes that have already been addressed, answers have been provided, and let's not reinvent the wheel until we have to, or that wheel's been proven it works sufficiently. And that's what we're going to be showing in the next section, is an example of exactly all of this, where Sammy Arbide from Western Allied is going to be showing you examples of doing these things. Multi-protocol, twisted pair, numerous other things. I'll let him get into it so I don't really show. And you'll be able to see those things actually in action. The strengths, some of the weaknesses, how it all goes together. So I hope you'll stick around for that next session next. We'll give you a little break here. And if there's any questions, I'm more than happy to answer them. Yeah, a lot of times that's what happens is, the question is, are we doing custom programming to these installations? Typically, the answer is yes. We do have some fixed apps, but we really, every installation is unique. So maybe 89% is the same. But there's that 10 to 20% margin that says we've got to have something unique. And therefore, now we can have the programming tools for these devices to allow you to create that custom functionality. The benefit with the programming, like you mentioned, is that you can gain better ownership of the customer, and you can make a better relationship with that customer through providing the appropriate solution that meets the requirements the best, and not just trying to kludge it together, but actually making it meet the requirements of what they need. You can, oh yeah, in fact, we don't really license it. We try to give it away for free. So that you can do the programming, you can have us do it, you can contract someone to do it, but you have that option to do whatever you want. Well, these are PLCs. Yeah, no, technically, industrial PLCs, no. These are distributed control devices, which when you look at PLCs and distributed control devices, they're on the same playing field now as far as what goes on, but these are distributed control devices. Mm-hmm.